My name is Dan Schrag. I'm the Sturgis Hooper Professor of Geology at Harvard University. I'm also Professor of Environmental Science and Engineering and Professor of Public Policy in the Harvard Kennedy School. In this session, we're going to talk about the question of land use, and in particular, the question of how we can balance the desire to expand our forests that are taking up carbon out of the atmosphere and reducing CO2 emissions versus the need that the energy transition has for additional land use, some for renewable energy, but mostly for biofuels, because it looks today like we're going to need biofuels to decarbonize part of the energy system that are really hard to electrify. One important issue with climate change is the interconnection between climate change and human land use. Here's a figure showing how the entire land surface of the Earth is divided into different categories. About a quarter of the land surface is essentially uninhabitable, either because there are ice sheets like in Greenland or Antarctica, or because the land is essentially barren, whether it's deserts or salt flats or something like that. Human settlements, cities, villages, and other human infrastructure actually accounts for a very tiny fraction, only about 1 million square kilometers of land surface. By far the largest category of human land use is agriculture, and nearly 80% of that is for livestock, essentially cattle grazing, accounting for something like 38 million square kilometers of land. In contrast, the land used for agriculture for growing crops is relatively small, only 10 million square kilometers. Still a huge amount, but tiny compared to the land used for livestock. There's also about 40 million square kilometers of land that are currently forested. These forests aren't all wild. Some of them are managed forests that are used for timber production or other forest products. There's also about 14 million square kilometers of shrubland and grassland. If we look at the history of carbon dioxide emissions since 1880, we of course see the huge increase in emissions coming from the growth of fossil fuel use, natural gas, oil, and coal. But you also see at the top of the graph the contribution to CO2 emissions from human land use. The dominant source of these emissions has been deforestation, essentially clearing forests to make room for agriculture. It's important to remember that overall, the land is still a net sink for carbon dioxide. That is, trees are taking up more carbon dioxide than are being released from deforestation. But if all of these emissions from land use, from deforestation and other activities hadn't occurred, then, of course, we'd have a lot less carbon in the atmosphere. It's not huge compared to fossil fuels, but it's still a significant contribution to global warming. On this map, you can see an estimate of the impact of human activities. In light green is the area that was originally forested before human activities. And in dark green is the area that's forested today. You can see huge changes across Western Europe, in Africa, and in Southeast Asia, and of course, in South America, around the edges of the Amazon. This deforestation has yielded agricultural land that has been critical to allowing us to feed the world's population. And yet it has also led to substantial carbon dioxide emissions that have contributed to global warming. In 2017, a paper was published on natural climate solutions. This was written by a large number of ecologists, many of whom worked for large conservation organizations like the Nature Conservancy or the World Resources Institute. This paper proposed something pretty radical, the idea that conservation efforts could actually contribute to climate change mitigation in a substantial way by taking up huge amounts of carbon dioxide, essentially reversing some of the land use impacts that had happened over the previous centuries. This wasn't an entirely new idea, but it was the scale of the claim that was so incredible. Griswold and his colleagues claimed that conservation efforts could actually take up almost 24 billion tons of carbon dioxide per year, nearly 60% of the global CO2 emissions. They recommended a wide variety of land use practices, including reforestation, avoided deforestation, natural forest management, and many other things. They also claimed that this could be done at a relatively low cost. I think subsequent work has shown that these claims were a little bit too ambitious. But that hasn't stopped conservation organizations from making substantial claims that conservation efforts contribute directly to climate mitigation. And they've tried to monetize those contributions by essentially selling carbon offsets for other types of carbon emissions from fossil fuels. A carbon offset is a reduction in CO2 emissions that offsets emissions happening somewhere else. Now, to be a legitimate offset, the carbon removal has to be essentially not regulated already by other laws. That is, it can't be covered by an emission reduction requirement that exists already. From the perspective of these conservation organizations, carbon offsets represented an incredible opportunity to get money from companies who wanted to reduce their emissions but found it too difficult to do so directly. The primary way that these offsets were facilitated was through a voluntary carbon market. Now, the voluntary carbon market allows an individual or an institution to offset their carbon emissions by essentially paying for a carbon credit from somewhere else. And many of these carbon credits are biological. That is, they represent conservation efforts around the world that are then sold into these markets. This graph shows how the voluntary market has grown in size from less than 50 million tons of CO2 in 2011 to almost 400 million tons of CO2 in 2021. This sounds like a big number, but remember that global emissions of CO2 are almost 40 billion tons. So this 400 million tons represents just 1% of annual emissions. In terms of dollar value, the voluntary carbon market has also grown enormously, jumping up to nearly $2 billion in 2021. Now, that seems like a big number, but it's important to remember that global investment in the energy industry was more than $2.5 trillion in 2023. And so $2 billion is still pretty tiny in comparison. So why hasn't the voluntary carbon offset market grown even faster? If these activities like reforestation or avoided deforestation really can remove CO2 from the atmosphere, why haven't we put much more money into them? The answer is that these offsets are incredibly problematic. They have a number of challenges, and so far they haven't been able to convince people that these are legitimate sources of CO2 reductions. One concern about carbon offsets is the issue of additionality. That is, whether the action, the protecting a forest or planting a tree, would have happened if you hadn't actually intervened. For a lot of biological carbon offsets associated with forests, this is really challenging. How does one really determine whether the deforestation would have occurred if you hadn't protected that particular part of the forest? Another major concern is the question of reversibility or permanence. For many biological carbon offsets, the lifetime of this intervention is supposed to last at least 100 years. But actually figuring out whether they really will last 100 years is a big concern. How do we know when a carbon offset is generated and a particular part of the forest is protected that somebody won't come 50 years from now and cut that forest down? And when that happens, how will that be made up in terms of overall carbon emissions? The other concern is that 100 years is not nearly long enough to deal with the lifetime of climate change. Carbon dioxide in the atmosphere lasts much, much longer than that. And so just protecting forests for 100 years is inadequate. A related concern to permanence has to do with measurement and monitoring of the offsets. Of course, it's essential to actually be able to measure what's happened on the ground. And advances in satellite technology and remote sensing has made a big difference in allowing us to know what's happening even in remote parts of the world. But there is still a question about long-term monitoring. who is charged with determining whether these carbon offsets will actually persist over centuries? A related issue is the question of enforcement. Who is in charge of making sure that these agreements between, say, a company and a conservation organization are actually legitimate? One of the fundamental problems with these biological carbon offsets is that both the buyer of the offsets, say the company who wants to reduce their emissions, and the seller of the offsets, the landowner who owns the forest, neither of them have much interest in actually finding out what really happened to the carbon. In the case of the buyer of the offsets, they've paid their money, they've gotten their carbon reduction, and frankly, they would like that to be the end of it. They don't want to know anything more. And in the case of the seller of the offsets, they've collected money in exchange for the carbon that's being stored in their trees, for example, and have no interest in discovering later that those trees have burned down or fallen down in a storm or been cut down, because then they would have to repay that money. And so this creates a very difficult challenge in terms of the structure of these voluntary markets. A final issue, and this may be the biggest problem with biological carbon offsets, has to do with something called leakage. Leakage is the idea that when you protect carbon somewhere, it will move somewhere else. For example, suppose I'm a conservation organization and I'm protecting a forest in Southeast Asia from timber harvesting. Does that mean that I've essentially reduced the emissions of CO2 to the atmosphere from deforestation? Not necessarily. If the timber companies that were operating in that region just move somewhere else and cut down the same amount of forest, I really haven't done anything to protect the atmosphere. I've protected a particular piece of land, but the actual deforestation has continued unabated, and therefore carbon emissions have continued to be just the same. And measuring that leakage turns out to be very, very challenging. So overall, while carbon offsets seem like a dream if you want to reduce your carbon emissions for very little money, but if you look in detail, you discover that these carbon offsets are not legitimate ways of reducing emissions. For example, in the California carbon market, that is a mandatory carbon market, not a voluntary one, they have biological carbon offsets associated with forestry and agriculture, and some studies have estimated that well more than half of those offsets are not legitimate. So there may be some potential for conservation to remove carbon from the atmosphere by reforestation or avoided deforestation, but actually monetizing it and making it into real policy turns out to be very, very challenging. The debate over carbon offsets and the potential effort to restore forests and take up more carbon in some ways loses sight of the bigger picture, which is that climate change is going to require a lot more intensive land use by human society. One effect may be from agriculture itself. We know that as temperatures rise, agricultural yields may decline. During heat waves in recent years, we've seen agricultural yields decline in particular regions. For example, in 2003 in Western Europe, we saw grain yields drop by more than 30%. The same happened in Russia in 2010 and in the US in 2012. There are some studies that project terrifying drops in agricultural yields as the earth warms, projecting potential food shortages for the world population. And yet, there are other experts who suggest that agricultural yields may increase, particularly in poorer countries that currently have very low agricultural yields because they don't use fertilizers or other modern agricultural methods. But if agricultural yields drop, that is, how much grain you can produce on a particular area of land, then the agricultural area required to grow the world's food supply may increase, and that may drive additional deforestation. But another potential driver of human appropriation of the land, potentially much, much bigger even than agriculture, is the use of biomass for energy directly. When we think about the overall decarbonization of our energy system, there are really three parts to the solution. First, we need to electrify as many different parts of our energy system as we can. And second, we need to decarbonize our electricity generating system. That will take care of a large fraction of our emissions. But the third part is just as important. And this has to do with parts of our energy system that we, at least right now, can't electrify. This includes many parts of our transportation system, like air transport or shipping or heavy trucks potentially, and also many industrial activities where it's very challenging to supply the needed energy with electricity alone. In all of these cases, we need some alternative fuels, usually liquid fuels, to supply the energy required to fly a jet airplane or to make a ship travel across the ocean. This figure shows the petroleum products that come from a barrel of crude oil in the US in 2022. You can see that the largest product, motor gasoline, accounts for a little less than half of the total barrel of oil. Other important parts are distillate, which is diesel fuel used for trucks or in some cases for ships or trains, jet fuel, and a variety of other products that include feedstocks for industry or residual fuel that's used for heating or for ship fuel. Right now, we think that electric vehicles will be able to displace most of the motor gasoline use in the future. It may take several decades for that to happen, but eventually we can get rid of maybe half of our oil consumption just from electrification. But what about these other sectors? And what about the heavy industry that is going to require alternative fuel sources? Right now, there are just a handful of potential alternatives to petroleum that could displace these hard-to-abate sectors in the future. One of them is hydrogen, either directly as hydrogen gas or potentially in some other chemical form like ammonia. Today, hydrogen is manufactured either from natural gas or from coal, primarily for refining of petroleum or for making ammonia for agricultural fertilizers. The idea for the future is that hydrogen could be made from electrolysis of water with clean electricity. We call this green hydrogen. Of course, there are huge land use issues associated with renewable energy directly. Now, the good news is some of that land area can be barren land, lands that don't have other uses, like deserts, for example. And wind farms can certainly exist on farmland where they don't interfere with the agricultural production of that land either. And hydroelectric dams, for example, also take up a huge amount of land as they cause flooding to create the artificial lakes. There are certainly some parts of the world where renewable energy development is challenging because they don't have enough land area. But in most of the world, renewable energy production can be accommodated without sacrificing huge amounts of forested land and other protected areas. An alternative would be that you could still make hydrogen from natural gas or coal, but sequester the carbon dioxide produced in the process, and that would be called blue hydrogen, also low carbon emissions, but still involving fossil fuels. The excitement around green hydrogen as an alternative energy source has grown incredibly quickly in just the last few years. Currently, there's nearly $600 billion of potential investments into low-carbon hydrogen, and more than 40 governments have published a hydrogen strategy for the future. The problem is that green hydrogen is currently very expensive to make. In some situations where there's very low-cost clean electricity, you can produce green hydrogen with electrolysis for as little as maybe $5 a kilogram. A kilogram of hydrogen is equivalent to a gallon of gasoline. This is still very expensive compared to hydrogen produced from natural gas or coal that can be made for somewhere between $1 and $2 a kilogram. Many different governments around the world are projecting that the costs of production of hydrogen will come down dramatically as more and more deployment of hydrogen electrolysis occurs. The US Department of Energy has a cost target for green hydrogen of $1 per kilogram in the near future. But the challenge is that the production costs of green hydrogen are not the only costs. Hydrogen gas as a fuel is much more difficult to store than natural gas or oil or coal, and that makes it very expensive. In addition, the distribution costs of hydrogen, moving it from one place to another, are much more expensive than for other fuels because hydrogen can make metals very brittle. You need special materials, and that is very expensive. If we think about what the delivered price of green hydrogen might be, we realize that it's going to be different for different sectors. For an industrial sector, like ammonia production, where an ammonia factory would run pretty much all of the time, the costs of storage and distribution don't have to be that high because you can build the ammonia plant right next to the source of the hydrogen production. If you wanted to use hydrogen as a backup power supply to help deal with the intermittency of wind and solar, so produce electricity when the wind isn't blowing or the sun isn't shining, then it becomes much more expensive because you need significant storage and distribution capacity. If you wanted to use hydrogen for heavy-duty freight transport, either for trucks or potentially for ships, that also would be extremely expensive, again, because of the high storage costs and also the high distribution costs, where you'd need to have hydrogen terminals distributed all over the country. Time will tell if the production costs of hydrogen do indeed come down in the future. But right now, hydrogen remains an incredibly expensive alternative to liquid fuels. We've recently done an estimate of what the carbon abatement cost of green hydrogen is by end-use sector. What we see is that even in the least expensive of the sectors, ammonia production, the cost is still more than $500 a ton. That's far higher than any price on carbon envisioned by policymakers in Europe, in the US, or anywhere else in the world. And for other sectors like steel production or cement production, using hydrogen to displace fossil fuels is much more expensive, well over $1,000 a ton, which looks pretty infeasible right now. Some people have suggested that instead of using hydrogen gas directly as a fuel, we convert the hydrogen to ammonia because it's much easier to transport the ammonia, and ultimately we can use the ammonia directly in a power plant or in a ship engine. Again, the problem with this is the cost. Currently, the price of ammonia made from natural gas in the US is about $350 to $400 a ton. A ton of ammonia is equivalent to about 2 barrels of oil on an energy basis. So that means that current ammonia, if you were to use it for a fuel, would be equivalent to $200 barrel of oil. That's pretty expensive. And green ammonia is much more expensive than ammonia made from natural gas. We think that green ammonia today would be about double the cost, or something like $700 to $800 a ton. Do we really think the world would stop using oil if it cost $300 to $400 a barrel of oil? That's a pretty high price to pay for carbon mitigation. Another option for liquid fuel for heavy transport or jet fuel might be biofuels. Now, biofuels play a significant role in our energy system today. For the US, this is in the form of corn ethanol. Back in the early 2000s, President George W. Bush, in an address to Congress, said that America was addicted to oil.
America is addicted to oil.
And proposed that aggressive investment in biofuels might be a solution. So biofuel production from corn grew with a 10% mandate from the federal government, meaning that 10% of all motor gasoline in the US today is from corn ethanol. Even more aggressive than the US has been Brazil, which doesn't produce quite as much ethanol as the US, but it's a much bigger fraction of their total energy supply. Brazil makes their ethanol from sugarcane, which is much more efficient because it has a much higher yield per hectare. Overall, the US and Brazil produce nearly 90% of total ethanol production, which is the majority of global biofuel production. Biofuel, particularly from corn ethanol, came under huge attack from the environmental movement, specifically in the US and in Europe. Environmentalists argued that the production of biofuel increased agricultural lands and destroyed forests, and also that the overall carbon emissions from the production of the biofuel were nearly as high as they were for petroleum itself. Indeed, careful studies from over a decade ago showed that the carbon emissions reductions from using corn ethanol were pretty marginal, maybe a 20% savings relative to motor gasoline. But corn ethanol production has improved. Ethanol refineries have become more efficient in terms of how much natural gas they use and also in how much ethanol they produce per unit of corn added. And that ultimately reduces their carbon footprint. Another big debate continues around what's called indirect land use. There's a question about what happens if we start using more corn or sugarcane for ethanol production. Does that mean that the demand for agricultural land goes up and therefore we cut down more forest and then we should be charged with those carbon emissions from deforestation? Or if corn yields are rising and we're producing more and more corn per unit of land, does that allow us to claim that reductions are decreasing? So amidst all of these difficulties with biofuels, why should we think that biofuels could be a potential solution to climate change? So could we just ramp up ethanol production from sugarcane and from corn so that the ethanol just replaced all of the liquid fuel that the world needs? The answer is almost certainly not. Global ethanol production today is around 30 billion gallons a year. Measured in terms of oil, that's roughly 2 million barrels of oil equivalent per day. Now, the world currently uses about 105 million barrels of oil a day. So 2 million barrels a day is a lot of fuel, but it's tiny compared to the world liquid fuel consumption. To meet our needs for aviation, for shipping, for trucking, for industry, we need a lot more fuel than that. The scale is enormous. Think of it this way. Currently, the U.S. uses about 40% of its corn harvest for ethanol production. There just isn't the arable land to grow that much corn or that much sugarcane to ramp up ethanol production by that large an amount. The other problem with ethanol is that it's actually not a great fuel. It has about a third less energy density as motor gasoline. And so you can't use ethanol in heavy trucks. You can't use ethanol to fly airplanes. And so for many applications, ethanol is just not the right fuel. You have to convert it to a more energy-dense fuel like kerosene for jet fuel or diesel fuel for trucks or ships. Ultimately, if biofuels are going to play an important role in helping to decarbonize the liquid fuel part of our economy, then we're going to have to get feedstocks that require very low inputs like fuel and fertilizers and pesticides. And we also need to be able to grow those feedstocks on land with low agricultural value because we're going to need the agricultural land for food. In an ideal world, those feedstocks would be from woody biomass. That is, instead of using just the sugar from the cane or the fruit from the corn, we would actually use the whole plant. We would select crops that grow as fast as possible with as few inputs as possible, and we would take the entire woody biomass and convert that to fuel. For a couple of decades, some people have explored the idea that you could use algae for biofuel. Algae have some advantages as a feedstock for fuel. For example, they grow at relatively high density, that is, a lot of biomass per unit area. You can grow algae in a relatively small pond and produce a lot of biomass. And second, algae have a lot of lipids, a lot of fat associated with their membranes, and therefore you can actually convert them to fuel relatively easily and produce a very high quality, high energy density fuel. Of course, the problem with algae is that aquaculture, unlike agriculture, is very expensive. Growing algae in a cement raceway or a pond is incredibly expensive. A ton of dry algae costs around $5,000, whereas a ton of biomass, hay or wood, costs maybe 100 times less. So there may still be some potential for biofuels from algae, but right now it looks like the cost is very, very high. If we're going to use woody feedstocks for biofuels, whether it's energy crops or wood chips or any other kind of biomass, including waste biomass. The question is, how do we then convert that biomass to a usable fuel? A classic way to do this is through a process called Fischer-Tropsch synthesis. Fischer-Tropsch was invented by two German scientists, Franz Fischer and Hans Tropsch, in the 1920s. It was deployed in Germany and then used extensively by Germany and Japan during World War II, converting coal as a feedstock into liquid fuel. And then in the 1980s, it was deployed in South Africa by Sasol, the South African oil company, during the embargo period where the world was not selling oil to South Africa because of apartheid. Sasol remains the largest Fischer-Tropsch company in the world. The idea of Fischer-Tropsch is to essentially break down the feedstock, whether it's coal or natural gas or biomass, into its most basic components, carbon monoxide and hydrogen. And from the carbon monoxide and hydrogen, which is often called a syngas, you can then manufacture synthetic molecules by passing them over a catalyst, which could be cobalt or iron, at relatively high temperature and pressure. And so through this process of passing the syngas over a catalyst, you produce all sorts of heavier organic molecules, which then can be used for synthetic fuel. Now, the great thing about Fischer-Tropsch fuels is that you can actually control the product you make. You can make incredibly clean-burning diesel fuel or jet fuel that has a much higher energy density than petroleum-based fuels. And is cleaner burning, it has lower particulates, extremely low sulfur content, and other pollutants that are common in conventional petroleum fuels. Now, the problem is that the way South Africa does it, converting coal into liquid fuel, the overall carbon footprint is about twice as high as it is from a regular barrel of petroleum. So currently, Fischer-Tropsch is probably the dirtiest technology in the world. But the irony is that if you actually fed biomass into the reactor instead of coal, you could actually make Fischer-Tropsch one of the most clean technologies in the world. Another advantage of Fischer-Tropsch is that carbon dioxide interferes with the reaction between the syngas and the catalyst. And so in a Fischer-Tropsch reactor, you have to remove the CO2 before the reaction takes place. This means that carbon dioxide produced as you convert woody biomass or coal into the syngas actually comes out in a concentrated stream, perfect for compression and storage underground. And so at relatively little extra cost, maybe $20 a ton or so, you can actually take the CO2 that comes out of the Fischer-Tropsch factory and store it underground. And that reduces the carbon footprint of Fischer-Tropsch fuels even more. And so if you actually could imagine a Fischer-Tropsch plant fed with woody biomass, converting that biomass into high-quality liquid fuels and sequestering the CO2, that would actually be carbon-negative fuels. It would actually be taking carbon out of the atmosphere because the woody material ultimately came from CO2 in the atmosphere through photosynthesis. Some of it is going into the fuel, but some of it is going into a geologic repository underground. The problem with Fischer-Tropsch, again though, like many of these technologies, is that the scale is enormous and the costs are really high. To make a Fischer-Tropsch plant be economical, it has to be really large. The plants in South Africa are more than 100,000 barrels a day. And the problem is, right now, we don't have a system to aggregate that much biomass in one place all throughout the year. For example, a large ethanol plant in the US might produce 1,000 to 2,000 barrels of oil equivalent ethanol per day. That's tiny compared to a petroleum refinery that might be 200,000 or 300,000 barrels of oil a day. So a Fischer-Tropsch plant is much more like a petroleum refinery. And the problem is, how do you get all that biomass and keep feeding it year round? Because to be economical, that factory has to run all the time. One answer to this may be that in the future, biofuel production will be dominated by tropical countries like Brazil and Malaysia. They have year-round growing season, lots of water, lots of sun, and biomass grows like crazy. So the yields per unit land area are incredibly high. But even so, building a very large Fischer-Tropsch plant to take biomass and convert it to fuel remains a really expensive thing to do. Another process that might be an interesting alternative to Fischer-Tropsch is to take woody biomass and put it in a pyrolysis reactor. Pyrolysis is essentially a way of converting biomass to fuel through heating it in the absence of oxygen. And in that process, there are essentially three products that come out of that. The pyrolysis reactor produces some charcoal or char, and that can be used as an energy source. It can be used as carbon black, or it can actually be incorporated into soils and where it will actually stay quite stable for thousands of years. So it'll be a long-term carbon sequestration method. The pyrolysis reactor also produces a certain amount of syngas that can also be used to burn and ultimately fuel the reactor. And then finally, the reaction produces some pyrolysis oil. And this pyrolysis oil is actually quite a lot like a petroleum crude. And so it's possible that that pyrolysis oil can be blended with conventional oil refineries and mixed into the general fuel supply. The reason that's an interesting idea is that it provides an opportunity to scale up the pyrolysis reaction without building a giant multi-billion-dollar plant. That is, smaller pyrolysis systems can be developed near where the sources of biomass are, and then the pyrolysis oil can be aggregated at conventional refineries. So it's a possible pathway to commercialization that's very interesting. But we're still in the early days of all of these technologies, and it is too early to pick exactly which technology is going to be the best one for converting woody biomass into fuel. But if biofuels has a future, it's got to be from taking woody feedstocks and converting them ultimately to high-quality fuels. Consider the special case of SAF, or sustainable aviation fuels. There's a lot of pressure on the airline industry today to come up with carbon-free solutions, so they essentially lower their carbon footprint of air transport. But the only solutions for them right now really involve biofuels. And there are a number of startup companies pioneering a variety of methods, and there are policies in Europe and in the US that essentially subsidize SAF production to try to scale it up to meaningful quantities. Right now, the majority of pathways to produce sustainable aviation fuel would come through conventional oils. What would be common in the US would be to use soybeans and convert the soybeans to soybean oil and then convert that oil to jet fuel. You can also use a variety of other waste oils and fats. You could, for example, as we talked about, use Fischer-Tropsch with either solid waste or potentially agricultural residue and waste or wood waste. Or you could even use Fischer-Tropsch, and instead of feeding in biomass or coal, you could feed in carbon dioxide and hydrogen. You could make green hydrogen and convert it to a fuel by taking carbon dioxide and hydrogen and combining them, although that is incredibly expensive. But again, when we get back to the issue of land area, the problem is there just isn't going to be enough land area to produce all of those soybeans to make oil to convert to jet fuel. The scale of global petroleum consumption is just too high, even just for jet fuel. And so ultimately, something like pyrolysis oil or some other mode of converting woody biomass into fuel is going to be required if we're ultimately going to lead to carbon-free aviation. So right now, as the world is scrambling to come up with new technologies to displace petroleum in our fuel supply, people are not really keeping sight of this emerging problem of competition for land. Yes, there's a lot of activism against biofuels because of the concern over competition with agricultural land, but I think the problem is much greater than that. Imagine if the world does come up with a really good technology for converting woody biomass into high-quality fuels for jet fuel, for diesel fuel, for shipping. What does that mean for our concerns about protecting biodiversity and keeping at least some of our land area of the planet protected? I think the answer is going to be really challenging in the years ahead. And we're going to see a bigger and bigger struggle between those people who really are concerned with biodiversity loss and conservation versus the people who want to see climate change mitigation and carbon reductions. Right now, it looks like they're on a collision course because if we look into the future, ultimately, decarbonizing the world may require a lot more land area. In some ways, this isn't really a surprise. You can think of fossil fuels as photosynthetic energy that's been accumulating for millions or even hundreds of millions of years. Algae or peat bogs integrated over geologic time that now we are using for energy in just a split second of geologic time, just the last century or two. And now, if we're going to say, okay, we're no longer going to use the time-integrated, accumulated photosynthetic energy that's happened over hundreds of millions of years, and instead we're going to require that we get it from photosynthetic material that is produced today, inevitably that's going to require more land area. So that puts us in a very challenging position. We want to reduce carbon emissions to minimize the impacts of climate change, and yet that may require us to use a huge amount of land in order to produce biofuels and displace petroleum. And then the question is, what is the trade-off with conservation? Because ultimately, we are conserving land to try to protect biodiversity. In some ways, the world's incredible biodiversity is caught in a very difficult situation between climate change and land use. And we're going to have to struggle with that in the century ahead.